Hey everyone, welcome back to another video. Right, I know it's been a while since I last uploaded, but I did just get my hands on a copy of the 2024, not 2024, sorry, the 2025 NHT methods exam, which just happened around 2 days ago. And I just wanted to go through it for all of you guys that wanted to look back and kind of compare your answers now that the Northern Hemisphere exams are done. Right now, I've heard this exam is quite tricky. I just looked through it. It does look a little bit difficult, but let's try our best to get through this. So let's start straight away with question one. And question one, as always for exam one, is asking us to find just a simple derivative. Now, how do we find this derivative? We're going to do quotient rule because it's a function divided by another function. So the way the quotient rule goes is bottom function times the derivative of the top function. The top function in this case is log base e of x, and the derivative of log base e of x is 1 over x, minus the bottom function, which is x cubed, times, sorry, what am I saying? Minus the top function, log base e of x, times the derivative of the bottom function, which is 3x squared. And that's all divided by the bottom function squared. Now, x cubed times 1 minus x, x cubed times 1 over x is just x squared. And then we have minus 3x squared log base e of x, all divided by x to the 6. We can simplify this a little bit more by taking out x squared as a common factor. And so we get left with this. One minus 3 times log base e of x, all divided by x to the 4. We're going to put a square around that just to show that is our final answer. Okay, 1a done. Let's move on to 1b. Right, so we have f of x is equal to sine of pi e to the 3x. Right, find f dash of 0. Let's first find f dash of x, which we can do through the chain rule. Right, so first let's take the derivative of the inside function, which is going to be 3 pi times e to the 3x. And then we multiply that by the derivative of the outside function, which is going to be cos of pi e to the 3x. Now f dash of 0, we just simply substitute 0 wherever we see an x. E to the 0 is just 1, so we get 3 pi times cos of pi. And cos of pi is just negative 1. If you remember from the unit circle, pi lands you here. That's when cos is negative 1, so we get negative 3 pi. Put a box around that just to show that is our final answer. Okay, not too bad so far. Next one is 3 marks, right? So let's read through this carefully. Let g of x equal ax cubed plus bx squared plus c, where a, b, and c are all real numbers. Right, so this is a cubic graph here. And h of x is equal to x squared over 4, so this is quadratic. The graph of g of x passes through the point 0, 9. Now, as soon as I hear that, the graph of g of x passes through the point 0, 9, I know that g of 0 is equal to 9. Now, what is g of 0? Well, you go back, you plug in 0 for x. It's really just c. And we know that this is equal to 9. So c is equal to 9. So we already have that. The graphs of g of x and h of x pass through the point 6, 9 and have the same gradient at this point. And they've shown both of these graphs below. Our job is to find the values of a, b, and c. right? So let's see how we can do this. First of all, we know that the graph of g of x goes through 6, 9. So we know that g of 6, right? And if we plug in 6 here, we get a times 6 cubed plus b times 6 squared, right? Plus c, but we know that c is 9, so we can just put plus 9. Now 6 cubed, that's just 36 times 6. Let's see what that's going to be. That's going to be 216. Right, so 216a plus b times 6 squared, and 6 squared is 36, so 36b plus 9, and we know that this is g of 6, and that's going to be equal to 9. Now, if I take this 9 over to the other side, let's see what happens. They're going to cancel, right? So 216a plus 36b is equal to 0. That's our first equation, right? The next very important thing is both of the graphs have the same gradient at this point right here. So what does that mean? The gradient of g of x, which is g dash of x, right? G dash of x. The gradient of g of x at x is equal to 6 is the same as the gradient of h of x at x is equal to 6. Right? That's going to be very useful to us. First, let's find g dash of x. Right? So if we go back, that's going to be 3ax squared plus 2bx. Let's find h dash of x as well while we're at it. So h dash of x is just going to be half times x. Now, g dash of 6 is going to be 3a times 6 squared plus 2b times 6. Now, that's going to be 36 times 3. That's going to be 108. So 108a plus 2 times 6, that's 12b. Right? G dash of 6 is 108a plus 12b. And we know that's equal to h dash of 6. Right? Now, h dash of 6 is really just 6 divided by 2. That's 3. So we have this. That's our second equation. Right? So let's take our first equation. 216a plus 36b is equal to 0. Let's take our second equation. Now, I want to find a way to cancel out these b's here, right? So what I'm going to do is, I'm going to multiply the bottom equation by 3. Okay, I'm going to multiply this entire thing by 3. So 108 times 3, we get 324a plus 36b is equal to 9. Remember, we multiplied the whole thing in the bottom by 3. And now if we minus this, right, we take the top one minus the bottom one, we get 216. We get 216 minus 324. So let's quickly do that. That's going to be negative 108. So negative 108a, right? The 36b's cancel out, is equal to negative 9. So a is equal to negative 9 over negative 108. That's just 9 over 108. And that's just going to be 1 over 12. So a is 1 over 12. We're going to substitute a is equal to 1 over 12 into, and let's do equation 2. So we get 108a, so 108a, but we know a, right? It's 1 over 12 plus 12b is equal to 3. Now, 108 times 1 over 12 is just 9. Take the 9 to the other side. Right, we get 3 minus 9, which is going to be negative 6. B is equal to negative 6 over 12. That's going to be negative a half. And we have our final answer. So A is equal to 1 over 12. B is equal to negative a half. C is equal to 9. Let's put a box around that. Okay, going at a good pace so far. So question 3a. Let f, right, they're going to define this function f. Let f of x equal half tan of x plus a half, where d is the maximal domain. Find the general solution for f of x is equal to 0. Okay, so half times tan of x plus half has to equal 0. Now, what can we do? We can multiply both sides by 2, right, just to get rid of the fractions. So we'll just do that. We'll multiply both sides by 2. So we get tan of x plus 1 is equal to 0. Tan of x is equal to negative 1. Now, how do we solve tan of x is equal to a, right, the general solution? That's going to be x is equal to n pi plus tan inverse of a, where n is an integer. Right, so we get x is equal to n pi plus tan inverse of negative 1. Right, now tan inverse of negative 1, you just have to think what angle makes tan become negative 1? Well, that's going to be negative pi on 4. Right, so we get this right here. So x is equal to n pi minus pi on 4, where n is an integer. Boom. That's that one done. Right, that's that one done right there. And we'll put a box around it just to show that is our final answer. Okay, let g of x be equal to sine of x plus a half. Find all values of x such that f of x is equal to g of x within this domain. Okay, so we'll do f of x. We'll do let f of x equal g of x. Now, f of x is half tan of x plus a half, and g of x is just sine of x plus a half. Right, so we can multiply both sides by 2. Right, so tan of x plus 1 is equal to 2 sine of x plus 1. The plus 1 and the plus 1 cancel out, so we get tan of x is equal to 2 sine of x. Now, how do we deal with this, right? Well, there's something quite clever we can do. We can rewrite tan of x as sine of x divided by cos of x. Now, let's multiply both sides by cos of x. Let's move it to the other side. So we get sine of x minus 2 cos of x sine of x is equal to 0. As you can see, we can factor out a sine of x. Using null factor law, we get sine of x is equal to 0, or 1 minus 2 cos of x is equal to 0. If you solve the general solution for sine of x is equal to 0, you'll get x is equal to n pi, where n is an integer, And if you solve this, you'll get cos of x has to equal a half. The general solution is going to be 2n pi plus or minus cos inverse of a half. Right now, cos inverse of a half, you're just thinking what angle makes cos become a half. That's going to be pi on 3. And n is an integer. Right? So we're solving this in the domain negative pi to pi. So let's just plug in a few values. Right? Let's plug in a few values. If n is equal to 0, then we get x is equal to 0 from this one. Or x is equal to plus or minus pi on 3. Right? Yep, that should work. Plus or minus pi on 3. Yep, that's all good. So we get x is equal to 0 or x is equal to plus or minus pi on 3. Let's try n is equal to 1. We get x is equal to pi or x is equal to 2 pi plus or minus pi on 3. Now, that is not going to work. These are not going to work. Right? These are not going to work here because they fall outside of the domain. Right? X is equal to pi is not in the domain. Right? It's round brackets. And 2 pi plus pi on 3 is not within the domain. And neither is 2 pi minus pi on 3. That's not within the domain either. So the only one that work, the only ones that work are x is equal to negative pi on 3, 0, pi on 3. There we go. Right, so we've done that one. Right, okay. Right now we have to, we have the graph of g of x below. On the set of axes below, sketch the graph of f of x over this interval. Now, tan of x has asymptotes at negative pi on 2 and pi on 2. We can see here that there's been no horizontal shift at all. They haven't horizontally shifted it. And they also haven't messed with the period, right? So they haven't done like tan of 2x or anything. So the asymptotes are going to remain at negative pi on 2 and make sure to label these, right? So x is equal to negative pi on 2 and also x is equal to pi on 2. Okay, now our graph, our tan of x graph, right? The y-intercept is just going to be 0, half, because if you put 0 in here, that becomes 0, that becomes 0, you just get left with a half. So they intersect at 0, half. Right, let's see where else they intersect. Right, so we know they intersect at x is equal to negative pi on 3. So first, let's figure out the scaling. Right, so this here, let's just call that a. So 3a, right, because a plus a plus a, that's 3a, is equal to pi on 2. That gets us to pi on 2. So a by itself is pi on 6. So each little, box is pi on 6, like this. Right, so each little horizontal step in the box is pi on 6. So we know that they intersect at negative pi on 3. Right, so let's find g of negative pi on 3. That's going to be sine of negative pi on 3 plus a half. And that's going to be negative root 3 on 2 plus a half. And that's actually just going to be 1 minus root 3 on 2. So at x is equal to pi on 3, which is going to be right here, because this one's pi on 6, this is pi on 3. Right, so at x is equal to pi on 3, they intersect right there. Sorry, oh my gosh. Right, oh my god. So this is pi on 6, this is negative pi on 3. This is negative pi on 6. They actually intersect here at negative pi on 3, right? Now, g of 0, we already did that one. We already did x is equal to 0, right? They intersect right there at the y-intercept. The next one is pi on 3. So we get sine of pi on 3 plus a half. Sine of pi on 3 is just root 3 on 2 plus a half. So we get root 3 plus 1 on 2. Okay, and our graph is going to look something like oops. Right, we also just forgot one thing, right? Let's find the x-intercepts of our graph. So we solve this general equation here. Right, we solve this general equation here. If we do n is equal to 0, we get negative pi on 4. So negative pi on 4 is going to be somewhere there, right? Right there. So we get so there we go. That's what it's going to look like. Make sure it doesn't touch the asymptotes. Right, something like that. Let's label our points. Pi on 3, comma, root 3 plus 1 on 2. We have 0, comma, half. We have the x-intercept, which is actually pi on, negative pi on 4, comma, 0. And we also have negative pi on 3, comma, I believe it was 1 minus root 3 on 2. Right? 1 minus root 3 on 2. Right, so that's our entire graph right there. You just have to use the stuff from the previous questions to sketch this one properly. Right, that was a pretty tricky one. Okay, question 4, starting with what it seems like probability. An orchid contains a large number of apples. 1/3 of the apples are bruised, so P is equal to 1/3. This is seeming like it's going to be a binomial formula kind of question. In a random sample of 4 apples, find the probability that exactly 3 are bruised. Okay, I'm going to say let x equal the number of bruised apples in this sample. Right, so x is a binomially distributed variable with 4 trials, right? So n is equal to 4 because it's a sample of 4 apples, and a probability success of 1/3. So find the probability that x is exactly equal to 3. We can do this formula, right? N choose x, so 4 choose 3, times the probability of success, which is 1/3, to the power of x, which is 3, times 1 minus 1/3, which is just going to be, 2/3, to the power of n minus x. Now, n is 4, x is 3, so 4 minus 3. Now, 4 choose 3. If you do the formula, and the formula is on the formula sheet, you'll just find that it's actually 4. So 4 times 1/3 cubed times 2/3. Now, 3 to the power of 3 is 27, so we get 4 times 1 over 27 times 2 over 3. So we get 8 over 27 times 3. Let's find out what that is. That's 81. So we get 8 over 81. Right? That is our final answer for that one. So let p hat be the random variable representing the proportion of bruised apples in random samples of 10 apples from the orchard. Find the probability that p hat is less than or equal to 1 over 10. Give your answer in the form 2 to the m divided by 3 to the n, where m and n are positive integers. Okay, so p hat is the proportion of bruised apples in the sample. So it's going to be, and before we do this, let's just do let x equal number of bruised apples in this sample. Right, so p hat is really just x, which is the number of bruised apples in the sample, divided by n, which is the sample size. Now n is 10 because it's samples of 10 apples. So x over 10. That's what p hat is. So probability that p hat is less than or equal to 1 over 10. That's the same as the probability that x over 10 is the less than or equal to 1 over 10. Because p hat is exactly equal to x over 10. So we can just replace it. Now, inside the probability, if you multiply by 10 on both sides, this is the same as the probability that x is less than or equal to 1. Now, if x is less than or equal to 1, and x is the number of bruised apples in the sample, that means we have the probability that x is equal to 0. You could have 0 bruised apples, or you could have exactly 1 bruised apple. So let's quickly apply the formula here. And x is a binomially distributed variable with 10 tries and a success probability of a third. Let's just double check that. Yep. So we get 10 choose 0 times a third to the 0 times 2/3 to the 10 plus 10 choose 1 times a third to the 1 times 2/3 to the 9. 10 choose 0 is just 1. A third to the power of 0 is just 1. So that right there is just 2 to the power of 10 divided by 3 to the power of 10. Now 10 choose 1 is just 10. A third to the power of 1 is just a third. And then the other one is going to be 2 to the power of 9 divided by 3 to the power of 9. So that turns into 10 times 2 to the power of 9 divided by 3 to the power of 10. So this turns into 2 to the power of 10 plus 10 times 2 to the power of 9, all divided by 3 to the power of 10. Right? Okay, let's take 2 to the 9 as a common factor from above. So we get 2 plus 10 that over 3 to the 10. That's just 2 to the 9 times 12 over 3 to the 10. Now 12, what's another way that we can write 12? Right? 12 is really just 4 times 3. And 4 is just 2 squared. So we get 2 squared times 3. So I'll just write 2 squared times 3, all divided by 3 to the 10. And now you can see why we did that. It's because it actually meshes in well with the other stuff that we have, right? We want everything to be in terms of 2 and 3 if we can. So 2 to the 9 times 2 squared, that's 2 to the 11. And then you cancel the 3 and the 3 to the 10, You get 3 to the 9. Let's check if it's in the right form. It is in the right form, and this should be our answer. Let me make a nicer little box to put it in. Okay, that was a pretty tricky one. 3 marks, right? A lot of working out and all that kind of stuff. Let's go to the next thing. So f of x is equal to e to the power of 2x, and g of x is equal to e to the power of x plus 2. Okay, find the x value of the point of intersection of the graph of f of x and g of x. Brilliant. Let's do let f of x equal g of x. So we get e to the 2x is equal to e to the x plus 2. Now it's very important here to recognize that e to the 2x is really just e to the x squared. This is a good little tip for the exam. If you see the same exact thing come up multiple times, right? I'm seeing e to the x repeated here multiple times. Try to make a substitution. It will usually make it easier, right? So let a equal e to the x. And this will become a lot easier now because you'll see what we get is a squared is equal to a plus 12. Now we get a squared minus a minus 12 is equal to 0. Okay, now we can use the quadratic formula. So negative b, so negative of negative 1 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 12, all divided by 2 times a, and a is 1. So we get 1 plus or minus the square root of 1 plus 48 divided by 2. 1 plus or minus the square root of 49 divided by 2. Let's bring this up here. Right, square root of 49 is just 7. So 1 plus or minus 7 divided by 2. So we have a is equal to 4, or a is equal to negative 3. Now we're going to reject a is equal to negative 3 because a is equal to e to the x, and the graph of e to the x is always greater than 0. It doesn't go negative. So we're going to reject a is equal to negative 3 because a is greater than 0. So we get a is equal to 4. Now we have to remember the question is not done yet. We have to solve for x, right? And a is equal to e to the x. Now solving e to the x is equal to 4. We get x is equal to log base e of 4. Right, let me get that in a nicer little box. And that's going to be our answer for this one, right? X is equal to log base e of 4. Okay. So let's go to the next one. Find the x value where the graphs of f of x and g of x minus 1 have equal gradients. Okay, I'm seeing g of x minus 1. I don't really like working with that too much, so I'm going to say let h of x equal g of x minus 1. Now, this has something to do with the gradients, right? So let's find the gradient. And first, actually, let's find h of x. That's g of x minus 1. So let's go back to g of x and just stuff in x minus 1 here. So e to the x minus 1 plus 2. Now h dash of x is going to be just e to the x minus 1. And f dash of x is just going to be 2 times e to the 2x. Now we want these to have equal gradients. So we want these two things to be the same. So e to the x minus 1 is equal to 2e to the power of 2x. Now, e to the x minus 1, it's very important to note that this is the same as e to the x times e to the minus 1. And again, e to the 2x is the same as e to the x squared. So once again, the same thing. I see, the same thing coming up multiple times. So I'm going to say let a equal e to the x. We get a times e to the negative 1 is equal to 2a squared. Then we get 2a squared minus a e to the negative 1 is equal to 0. Right, if I just take this to the other side. Then we can factor out an a, and we get 2a minus e to the negative 1 is equal to 0. Null factor law, a is equal to 0, or 2a minus e to the negative 1 is equal to 0. Now, a is equal to 0, we just talked about this, right? The graph never goes to 0 or below 0, so we reject as a is greater than 0. And if we solve this one, we get a is equal to e to the minus 1 over 2. Right? That's just going to be 1 over 2e. Now, the question isn't done yet because a is equal to e to the x. Right? E to the x has to equal 1 over 2e. So x has to equal log base e of 1 over 2e. That's the same as log base e of 2e to the negative 1. That's going to be the same as negative log base e of 2e. Right now, log base e of 2e is just the same as log base e of 2 plus log base e of e. Now, log base e of e is just 1. Oops, I think the thing is just shut off for some reason, right? Not sure why. Let's go back. Right, so log base e of e is just 1. So we get negative 1 minus log base e of 2. And that's going to be our answer for this one, right? So not too tricky, but not too easy either. Some of these were a little bit tricky, right? So that's the thing for these ones. Okay, this is seeming like a probability question. So a high jumper has up to 3 attempts to jump over a bar at a specific height. Once one attempt is successful, the high jumper does not make another attempt at this height. So at this height, let A be the event that the high jumper's first jump is successful, B be the event that the high jumper's second attempt is successful, and C be the event that the high jumper's third attempt is successful. The probability of A is 0.6, and the probability of B, given that A did not occur, or A complement, is equal to 0.5. Let n be a discrete random variable representing the number of attempts the high jumper makes at this height. Complete the table below for the probability distribution of n. Okay, let's try to make a little tree diagram, right? So the high jumper makes his first attempt. It could either be successful, which is event A, or it could be not successful, which is A complement. Now the probability of it being successful is 0.6 because they told us that. So the probability of it not being successful is 0.4. Successful, right? I can't speak today. 0.4. Okay, but the thing is, if he makes the first attempt, right? The first attempt is successful, he won't jump anymore. So the tree diagram on that side kind of just stops, right? But if he fails on the first one, then it continues on. After that, he could have the second attempt be successful or it not be successful. And this right here, what's going to go there is the probability of B given not A, right? And they told us that's 0.5. So the other one also has to be 0.5. Once again, if he's successful on the second attempt, right, so we're here, the tree diagram is going to stop there because you don't make another attempt, right, once one attempt is successful. But if it's not successful, finally what we could have is either the third attempt is successful or the third attempt is not successful. And this tree diagram is going to help us a lot in doing this question. So the probability that n is equal to 2, meaning the number of attempts the jumper makes is 2. The only way that could happen is if we go down this branch right here. Right, so 0.4 times 0.5. And if you do that, that'll be 0.2. Now you may be wondering, how do I find out the probability of there being 3 attempts, right? And I would say you don't need to do any sort of fancy thinking or, any of that stuff that we just did, right? All you need to do is recognize that this is actually a probability distribution. So all the probabilities have to add up to 1. So 0.6 plus 0.2, 0.6 plus 0.2, plus whatever that probability is, let's call it x, has to equal 1. So 0.8 plus x has to equal 1. So x has to equal 0.2. So let's put that in, right? The wording of this question is a little bit tricky, but we've got that one. The next one says to find E of n, the mean number of attempts the high jumper makes at this height. So E of n, all we need to do is just take the n value and multiply by its corresponding probability. So 1 times 0.6 plus 2 times 0.2 plus 3 times 0.2. So 0.6 plus 0.4 plus 0.6. And this is 1.6. That's going to be our mean, E of n. Okay, now this one is probably the hardest question on the exam in my opinion, right? The wording makes it quite tricky. So the high jumper was not successful on the first attempt at this height. That is really, really crucial, right? So what's given to us? What's given? The first attempt was not successful. That means what's given is A complement. Find probability of C given B complement, given that the jumper has a 0.7 probability of making a successful jump on either their second or third attempt. Okay, let's dissect this. So probability of C given B complement, right? Let's write this a bit more accurately, because we're trying to find the probability of C given that B did not occur, right? And A did not occur, because A is also a given, right? So they're asking us to really find probability of C given that B did not occur and A did not occur, right? Because this is also a given. So that's what we have to find, right? Let's see what else is given. So the probability of making a successful jump on their second attempt, which is B, the event B, or their third attempt, which is C, right? And this is all given that A did not occur, is equal to 0.7. Right? So let's try to find this now. Let's use the conditional probability formula. So we get probability of B or C intersection A complement divided by the probability of A complement is equal to 0.7. Right? Okay. Now we know the probability of A complement, right, from above, and that's really just 0.4. So we get the probability of B or C intersection A complement is equal to 0.7 times 0.4, which should be 0.28. Right, if we want to do it 7 over 10 times 4 over 10, that's going to be 28 over 100, right? So that's just going to be 0.28. Okay, but what does this actually tell us, right? Let's draw a little Venn diagram here. Now you might be wondering, hold on a second. There's A, B, and C, but why have I drawn them all disconnected from each other? Right? Usually when you see a Venn diagram, it usually looks something like this. So why the heck have I drawn it like this? Right? And the answer is because these events cannot occur simultaneously. Right? Let's talk about what I mean by that. The probability of A intersection B is 0. Right? Because you can't have your first attempt be successful and your second attempt be successful. Because once your first attempt is successful, you don't do a second attempt, right? The same goes for probability B and C. The same goes for A and C, right? So everything is disjoint. So B or C, so B union C, B or C, represents this. A complement represents this. It just represents everything that's not A. Now, where do those two overlap? Where do they intersect? Well, they just intersect at the orange parts, right? So we get probability of B plus the probability of C, right? So the intersection points is really just, right, if I just get rid of all this stuff here, the intersection points, as you could see, really were just the B and C circle. So this weird, complicated looking thing is just probability of B plus the probability of C, and that has to equal 0.28. Now, what is the probability of B? Right? Well, the probability of B would just be if we go down this kind of route here, right? Because B is the event that the second attempt is successful. If you go down this route, the second attempt is successful. So it's going to be 0.4 times 0.5, which is 0.2. So we find that the probability of C is really just 0.08. Right? Okay. And now to find this right here. We know that the probability of C, which is the third attempt being successful, is really just the probability of not A multiplied by the probability of not B given not A, right? So probability of not A, that's this, times the probability of not B given that A did not occur either, right? So probability of B given not A times the probability of C given that A did not occur and B did not occur, right? So that's going to be whatever goes here, right? So we know probability of C is 0.08. Probability of not A is 0.4. Probability of not B given not A is 0.5. And finally, that's the thing that we're trying to find. Now 0.4 times 0.5 is just 0.2. And so if you divide both sides by 0.2, we get probability of C given not A and not B which is what we wanted to find, is going to be 0.08 divided by 0.2. Let me just get rid of this, right? Divided by 0.2, that's going to be 0.4. And that's going to be our final answer, right? Now, that was quite the tricky question with wording and working out and everything, but we got there in the end, right? So the crucial steps to this question is recognizing this Venn diagram and also making this tree diagram, right? Both things will really help a lot. Let's go on to the next one. Okay, f of x is equal to x squared plus bx minus 6. Find the values of b, and also, sorry, b is a real number, right? Find the values of b for which the two solutions of f of x is equal to 0 have a difference of 5. Okay, let's let f of x equal to 0. So we get x squared plus bx minus 6 is equal to 0. We can solve this using the quadratic formula, right? Negative b plus or minus the square root of b squared minus 4 times a in this case is 1, c in this case is negative 6, all divided by 2 times a, and a is 1. So negative b plus or minus the square root of b squared plus 24 divided by 2. That's going to be our two x-intercepts, right? Now, I want you to think very, very carefully about this. Right? Let's say we have our graph of f of x here, right? Just drew a random sort of quadratic graph. This one right here is going to be negative b plus the square root of b squared plus 24 over 2. That's going to be that x-intercept. And the other one is going to be negative b minus square root of b squared plus 24 over 2, right? Because negative b minus the thing is going to be smaller than negative b plus the thing, right? So, okay. Now let's talk about this. So how do we find the difference between these two? This is the difference between these two. Well, all we really do is we take negative b plus the square root of b squared plus 24 over 2, and we minus negative b minus the square root of b squared plus 24 over 2. Now, what's that going to be? Negative b plus square root of b squared plus 24, and we get plus b plus square root of b squared plus 24. All divided by 2. And now negative b and plus b will cancel out, and we get this thing plus the same thing. So we just get 2 times square root of b squared plus 24 divided by 2. That's just b squared plus 24. So the difference between the two is actually just b square root of b squared plus 24. And we want the difference to be 5. So squaring both sides, we get b squared plus 24 is equal to 25. B squared is equal to 1. And we get b is equal to plus or minus 1. Now that works because b can be any real number. And they said find the values of b, right? Not just the value, but the values. So we have 2 values here. So that works. Okay, let b be less than 0. Explain why an inverse function does not exist when f is restricted to the domain 0 to infinity. Okay, b is less than 0, so b is a negative number. The x-coordinate of the turning point of the graph is going to be negative b over 2a, right? Most of the time they call that the equation for the axis of symmetry, right? That's really just the x-coordinate of the turning point, which is going to be negative b over 2a, right? So let's think about this. If b is less than 0, meaning it's an element of negative infinity to 0, right? Then what's going to happen? Then negative b is going to be a positive number, right? And also, just by the way, a here in this case is just 1, right? So right, negative b over 2. So the turning point, the x-coordinate of the turning point is negative b over 2. Right? Now let me put the negative here. Now if b is less than 0, then negative b, right? If b is less than 0, then negative b is greater than 0. Right? And if negative b is greater than 0, then negative b divided by 2 is also greater than 0. So in short, negative b divided by 2, which is the x-coordinate of the turning point, is greater than 0. Right? So therefore, as the turning point would be within the domain of f, which is also 0 to infinity, f of x would not be 1 to 1. This means that f inverse of x would not exist. Okay, so that's what we have. The x-coordinate of the turning point would be within the domain. This would mean that the turning point is within the domain, and that means that f of x is not going to be 1 to 1, so it's not going to have an inverse function. Right, so that one's not too bad. Find the rule for the inverse function of f when f is restricted to the domain of negative infinity to 0. Okay, let's try this. First, we're going to say let y equal f of x. So we get y is equal to x squared plus bx minus 6, right? So we get this right here. Now, before I do anything, it's really, really crucial to know that to find the inverse function of a quadratic like this, what we actually have to do is we have to complete the square, right? So first we're going to complete the square on this. Right? Okay, so I've completed the square. And now for inverse, we swap x and y. Right? So we get y plus b over 2 squared minus b squared over 4 minus 6 is equal to x. And now we're going to solve for y. Right? So we get y plus b over 2 squared is equal to x plus b squared over 4 plus 6. Right? Now we take the square root on both sides, remembering to take the plus or minus as we take the square root. And now we get y is equal to negative b on 2 plus or minus square root of x plus b squared over 4 plus 6. Now you can see we actually got two different things here. We got a plus version, a negative b on 2 plus this thing, and a negative b on 2 minus this thing. right? So we're going to need to reject one of them. We only have one inverse function, right? So we're going to have to reject one of them. How do we figure out which one to reject? Well, f in this case has a domain of negative infinity to 0. So the domain of f in this case is negative infinity to 0, right? The range of the inverse is always the domain of the original. So the range of the inverse has to be negative infinity to 0. Now, which one of these graphs can have a range of negative infinity to 0? Well, let's see. So don't be scared, right? B is just like a number. It's like a parameter, right? So if I graph this, right, the positive version would look something like this, right? It looks something like, you know, like that. The positive version is going to look something like that. And the negative version is going to look something like that. Now, which graph can have a range of negative infinity to 0? Well, that has to be the negative version. So we're going to reject y is equal to negative b over 2 plus square root of x plus b squared on 4 plus 6. Right? So therefore, the inverse function, and let's make sure we only need the rule and not the domain or anything. Yep, so we just need a rule. Therefore, the inverse function is going to be negative b on 2 minus the square root of x plus b squared over 4 plus 6. And we're going to put a little box around that. Right? That's going to be our final answer for that one. So that one was pretty tricky. Right? That one was pretty tricky. Let's go into part C. So let g be a function with maximal domain, and the rule g of x is equal to log base e of negative x minus 2. Find the value of b for which the maximal domain of the composite function, g composed of f, so g composed of f is just g of f of x, right? And we need the maximal domain of this function here, this composite function, to be negative 2 to 2, non-inclusive. Okay, let's find this composite function first. So you just take g, and wherever you see an x, you just put f of x there. So negative x squared plus bx minus 6 minus 2. That's going to be negative x squared minus bx plus 6 minus 2. That's going to be negative x squared minus bx plus 4. Right now, how would you usually find the domain of this graph right here? Right? If I just asked you, hey, what's the domain of this graph? What would you usually do? I'm guessing what most people would do is they would find when the inside function is greater than 0, because anything inside a log has to be greater than 0, right? So they would find when this is greater than 0, then they would get some x values, and that would be your domain. This time we're going to go backwards, right? So we have the domain here, which is negative 2 to 2, and we want the graph, the inside graph, to be greater than 0 only for negative 2 to 2. Now, this is a negative x squared graph, so it's going to look something like this, right? What's the only way it could be greater than 0 for negative 2 to 2? That's if this intercept is negative 2, and this intercept is 2. Then you can see that, the graph is greater than 0 only from negative 2 to 2, non-inclusive. Because at negative 2 and 2, it's exactly 0. Right? So for this inside graph, when we plug in 2, we want it to be exactly 0. Right? We want x is equal to 2 to be an intercept. Right? So we get negative 4 minus 2b plus 4 is equal to 0. Negative 4 and plus 4 cancel. Negative 2b is equal to 0. B is equal to 0. Right? Now, we can just leave it here, but let's just double check. Right? We also need negative 2 to be an intercept. So if we put in negative 2, so we get negative 4 plus 2b plus 4 is equal to 0. Negative 4 and 4 cancel. 2b is equal to 0. B is equal to 0. And so we get b is equal to 0. That's going to be our final answer, right? That's what makes the maximal domain of this composite function be negative 2 to 2, non-inclusive. Right, so that was some bit of a conceptual one, right? A bit of a tricky one. Let's try this. The last question on the exam, question 8. So f is a function from 0 to infinity for a domain, where f of x is equal to x over 2 times square root of x plus k, where k is a positive real number. We're going to consider the particular case when k is equal to 6. Show that the derivative with respect to x of x times square root of x plus 6 is equal to square root of x plus 6 plus x over 2 times square root of x plus 6. That's a mouthful, right? But for these show that questions, usually we want to focus on the left-hand side, which is the derivative of x times square root of x plus 6. Now that's the same as x times x plus 6 to the half. And you want to do product rule, right? So the first function times the derivative of the second function plus the second function times the derivative of the first function, which is just 1. Now, anything to the power of a half. All right, sorry, I forgot this here. Now, anything to the power of half or negative half, right? X to the power of half is root x. X to the power of negative half is 1 over root x. Right? So let's just apply that here. We get x over 2 times x plus 6 to the negative half plus x plus 6 to the half. So we get x over 2 times 1 over root x plus 6 plus root x plus 6. And that's really just root x plus 6 plus x over 2 times, sorry, it's just x over root over 2 root x plus 6. Now the right-hand side is just x root x plus 6 plus x over 2 root x plus 6. Here we can see, after doing the product rule, the left-hand side is equal to the right-hand side. So therefore, the derivative of that thing there is equal to the stuff on the right-hand side. And that's how you usually want to approach these show that questions. Right? Let's put a little box around it. Okay, hence or otherwise, evaluate the definite integral from 0 to 6 f of x dx. Okay, let's see how we can do this, right? First of all, we're given this piece of information, which is very, very important, right? If the derivative of this is equal to this, then the antiderivative of the thing on the right-hand side right? The antiderivative of the thing on the right-hand side should just be what's on the left-hand side. Okay, we can split up this integral. And now you might notice this right here is really just f of x when k is equal to 6, right? Which is what we have. So we just want to solve for this integral by itself. Okay, so the integral or antiderivative of square root of x plus 6, we can rewrite that as antiderivative of x plus 6 to the half. And how do you do that? Well, it's going to be 1 over whatever is in front of the x, which is just 1, times n plus 1. N is this number right here. So half plus 1. That's just going to be 3 over 2 times x plus 6 to the half plus 1. So that's going to be 2 over 3 times x plus 6 times x plus 6 to the 3 over 2. So we get x root x plus 6 minus 2 over 3 times x plus 6 to the 3 over 2. Right? Okay. Now let's actually evaluate this from 0 to 6. Dx, right? So we get the antiderivative that we got there. I don't know why that's just typed a letter there, right? Going from 0 to 6. So we get 6 times 6 plus 6, which is 12, minus 2 over 3 times 6 plus 6, which is also 12, to the power of 3 over 2, minus, now we plug in 0, so we just get negative 2 over 3 times 6 to the 3 over 2. Now, 12 to the 3 over 2 is the same as 12 to the half cubed, right? So it's the same as root 12 cubed. That's just root 12 times root 12 times root 12. That's just going to be 12 root 12. Okay, so we get minus 2 on 3 times 12 root 12 plus 2 on 3. Now 6 to the power of 3 over 2 follows a very similar logic. That's just going to be 6 times root 6. Right, let me get rid of all this gibberish stuff here, just so it looks a bit nicer. Now, okay. Now we can do a little bit of cancellation. So we get negative 8 root 12. And then we get 4 root 6. And so we get negative 2 root 12 plus 4 root 6. Now root 12 is the same as root 4 times 3. So that's 2 root 3. So we can do negative 4 root 3 plus 4 root 6. So it's really just 4 root 6 minus 4 root 3. And that's our final answer. Right, so definitely a bit of hefty working out, but we got there in the end, once again. Okay, a 2-mark question, the final question on the exam. Find the integral from 0 to k for x over x over 2 times square root of x plus k. Dx. Right, now the reason we're putting k here and not 6 instead of k is because this k is equal to 6 hangs over the entirety of question A, right? Part A. It hangs over the entirety of part A, but now we're in part B. So we're back just to this, right? Where k is a positive real number. But as you can see, we can apply something very, very similar. right? So instead of putting a 6 there, we can just replace that with k, and everything should work out the exact same. So this is going to be x times root x plus k minus 2 over 3 times x plus 6 x plus 6 to the 3 over 2. Sorry, not 6. That's going to be k. Right, so we replace the 6 with a k. And then we simply just want to evaluate this from 0 to k. So let's start with this. We get k times root 2k minus 2 over 3 times 2k to the 3 over 2 minus, and when you put in 0, you just get negative 2 over 3 k to the 3 over 2. Now, root 2k, you can split up as root 2 times root k, right? So you can do k times root 2 times root k minus 2 over 3 root 2k cubed, right? Minus, oh, sorry, not minus, that's going to be plus, right? Because double negative. Plus 2 over 3 times root k to the 3 over 2. So we get k root 2, and I'm not sure why it's put a letter there again, right? Not sure why it's put a letter there again. But we get k times root 2, root k, minus 2 over 3. And now we remember that root 2k cubed is just root 2k times root 2k times root 2k. That's just 2k times root 2k. So we get 2k times root 2k plus 2 over 3 times k times root k. Right? Because you do the same thing with the root k that you did with the root 2k. Then you get k times root 2 times root k minus 4k over 3 times root 2k plus 2k over 3 times root k. And now we get k times root 2 times k minus 4k over 3 root 2 root k plus 2k over 3 root k. And now you'll notice that we can actually take out k root k out of this, right? You get root 2 minus 4 root 2 over 3, right? 4 root 2 over 3 plus 2 over 3. Right? So we get here 3 root 2 over 3 minus 4 root 2 over 3 plus 2 over 3. That's just going to be, so that's just going to be negative root 2 plus 2 over 3. So this is the same as 2 minus root 2 over 3 times k root k. And as we can see, it's in the same format, right? We have an integer, positive integer, right? A minus root a, 2 minus root 2, all divided by b, which is 3, and then times k root k. So everything is in the right form, and that's going to be our final answer. Right? That is actually the end of the exam, right? Thank you guys so much for watching. I'm also going to try to do an exam 2 video, but we'll see how it goes. Right? I definitely think this is the hardest exam one they've put out in a while. Right? But thank you guys so much for watching, and I'll see you in the next one. See ya.